Okay, we are working our way up towards being able to do rigid body problems. Um, and there's kind of two more things that we need to do before we can do real rigid body problems. The first one is I have to define this thing called couples. Um, and then the second thing that I have to do is go through a list of what kind of loads are applied by, each kind of joint so that you can look at a plate that's on the floor with wheels and connected to a cable and whatever, and replace those joints with loads in your free body diagram, and then we can go to the calculations. Um, so I'm going to define couples first, and then I'll go through like a 3D example, and then we'll start talking about joints. So what this really is the moment of a couple, but people just call it a couple. So I'll write it like this: moment of a couple. And one of the most fundamental facts about moments, we defined those last time, is that a moment is dependent on the about point. If you change the about point, generally you change the moment. Okay? Um, so those were moments of a force that we defined last time, and moments of a force depend on the about point. About point. Uh, yeah, well, it was this definition. So the moment for an about point that we'll call A is equal to, and it's a vector, it's equal to the row vector crossed with the force. And the row vector is a vector that goes from the about point to the point where the force is applied. So that's P minus A. And so you could also expand this and write it as, as P minus A crossed with F. Okay, that P minus A is mathematically a way of saying a vector going from A to P. So does the moment of a force depend on the about point? Yeah, and because you can see it right there in the equation that A, it's there and you can't do anything about it. Yeah, that's right. It's it's a type of load that makes things rotate. Um, but a couple, um, so let me define a couple. Um, is two equal and opposite forces acting at a distance from each other. And so it makes sense to call this a couple. It's two things that are sort of work in tandem. And I want you to first think about the fact that, so let me draw, so here's some object, and let's say that there is, at this point P1, let's say that there's a force F1 acting on it. And at some other point P2, there's a force with the same magnitude. I want to try to make it look more parallel. Okay, I'll take that one. Same magnitude, opposite direction. This is F2, okay? And the key thing here is that F2 is, well, F1 is equal to negative F2, or vice versa. They're opposites of each other, okay? You get one of those forces by multiplying the other one by -1, okay? And so,
for a couple, do the forces have to be equal and opposite?
yeah, yep. So that's the definition of a couple. Like, keep that in mind. That'll be on a quiz, you know. Yes. And the kind of surprising fact. Oh, I wanted to say one thing about intuitively. Like, look at this picture. Okay. Imagine that this blob is a football player, and F1 and F2 are two defensive football players. You know, one hits high and one hits low, or whatever. The tendency of that couple is to cause a rotation of that blob. Okay. That makes sense, right? Yes.
So, like you said, they make rotation. Are they perpendicular? Like, if you draw a line between them, like, does it need to go through that?
No, it doesn't have to be perpendicular. They can be anywhere.
And with 3D, like, does that also work in 3D?
Yeah.
So they only have to be the same magnitude and different directions?
Opposite directions, specifically opposite directions. It can't just be this way and this way or whatever, you know.
Oh.
Yes.
They need to be equidistant from the about point? Or do you need to...
No, they don't. I haven't even defined an about point yet. But there is an important thing with relationship between couples and about points. So couples are a special thing, and come back. No, wrong class. So I'll show that the moment of a couple, you know, the moment produced by a couple does not depend on the about point.
Does it depend on the center of mass? Because I'm thinking
Nope.
of like a big long 2x4, and if I apply equal opposite forces, but at different distances from the center, won't that...
Nope, it doesn't. So this is the thing I want you to think about right now. Okay, and so because, so what's the net force of a couple first of all? You know, what's the net force that a couple produces? They're equal and opposite forces, so there's no net force, okay? We'll see that there is a net couple, but that couple doesn't depend on the about point. And so when we talk about couples, even though what a couple really is a pair of forces, we'll think about couples as like a pure moment, okay? It's a moment you could just add on no matter what your about point is.
So it doesn't depend on the location of P at all?
It depends on the location of P, but not the location of A. So I'll just think of it as a pure moment whose value doesn't change for different about points. One, like, you can think of a screwdriver as something that applies a couple. Like when you use a screwdriver, you're applying a couple to a screw. It's really an infinite set of couples, but the outside of the screwdriver is applying a force. If you have it horizontal, think of the slot being horizontal. and you turn it, the side over here is applying a force that way. The side over here is applying an equal and opposite force that way. And so it doesn't have a tendency, as long as you apply it symmetrically, it doesn't have a tendency to bend the screw or anything. All it has a tendency to do is turn it, and for me, strip the... Okay, so let's do this calculation. So what I said right there is all you have to remember about couples, but it's a really easy calculation to show why this is, to make sense out of why it doesn't depend on the about point. So I'm going to just think of this as a proof. Okay. So in here, let's choose an about point. Okay. And what we're going to see is that when we derive the moment produced by this couple, A is going to disappear from the equation. It's going to disappear from the calculation. And that's how we're going to see, like, it doesn't depend on it. You could make it 50, you could make it 100 and whatever. It just doesn't come into it. So this is going to be the row vector for force 1. And this is the row vector for force 2, just using the definition of the row vectors. And the moment, the total moment produced by the couple, for now I'm going to put A in there, because all we're doing is calculating the moment for one force, calculate the moment for the other force, and then we're going to add them up. So this is equal to row 1 crossed with F1. And then we're going to add to it the moment produced by the other one, row 2 crossed with F2.
That gives us a scalar, not a vector.
Cross products give you a vector. Dot products give you a scalar. Okay, so MA, if I expand this, is equal to P1 minus, so that row 1 is P1 minus A. And we're crossing it with F1. And then row 2 is P2 minus A. And that force F2 is equal and opposite to F1, so I'm going to write this as negative F1. And now you can distribute that cross product. Cross product does that just fine. So MA is equal to P1 cross F1 minus A cross F1 plus P2 crossed with negative F1 minus A crossed with negative F1. And now you can pull the negatives through. Cross product, that works fine too. So MA is equal to P1 cross F1 minus A cross F1 minus P2 cross F1. And then this is a double negative, so plus A cross F1. And now we have a positive A cross F1 and a negative A cross F1, so those cancel each other. And that's the only place that A showed up. So now A is totally out of this calculation. So when we did this cancellation, there's no more A dependence. And now I can clean it up a little bit, but the result is I'm going to take A off of this moment because it doesn't matter anymore. And I'm going to regroup these and write it as P1 minus P2 quantity crossed with F1. Okay. That's a formula you can use, but that's not going to be something we need in this class. What really matters is that for a couple, that moment, no matter what the about point is, it's the same thing. It's just a pure moment that you add into the rotational Newton second law. Okay, so let's do a 2D example. Anybody have any questions about that proof? I mean, I don't think it's too uncommon for engineering type people to see somebody go through a proof and just think like, now's the time that I can daydream for a while, and just tell me when you give me the answer or whatever, So there's the answer. But derivations can be really helpful in just like really wrapping your head around under what conditions equations work, what it is about, the equation that makes it work this way. So it is sometimes helpful. But to make proofs work for you, you have to use them to understand the restrictions on why the proof works, what are the specific instances where this equation works, that kind of thing. So anyways, all right, so let's do an example. So let's take a board. This is a 2D example. And let's say that there is a couple over here, and I'll write it like this, of 60 Newton meters. And then over here, there is a force. Let me give this some angle. So let's say it makes a 50-degree angle with the horizontal and has a magnitude of 200 newtons. And then we'll say, let's see, well, that's going to, so I'm going to have an unknown force here. I'll call this R. And then an unknown force let's see. I made this a little too tricky for myself. I hope this is going to work out. But let's say that there's an unknown normal force down there. And let's say that this has a length of 0.5 meters, and this has a distance of 0.2 meters. And we want to calculate.
Wait, does the weight matter or no?
Yeah, let's give it a mass. So let's say the mass is 10 kilograms. Okay, we're going to calculate the R vector and the normal force. So you have to choose an about point. You can choose any point you want. So I'll choose this as my about point, that red dot. And now I'm going to go through, this is already a free body diagram, so I'll go right into making the table. So there's rho, force, moment. Oh yeah, it's not a free body diagram yet. There's the 10 times 9.81, so this is 98.1.
So the mass is 10 kilograms?
Yeah.
Okay.
Okay, and I'll start with the R vector. What's the row vector from the red dot to R? Right, 0. The force vector is Rx, Ry. This is in the plane, so the Z is 0. And then the cross product of those two is zeros.
Where's M?
What?
Where's M?
M is the moment produced by that force. And you get that by taking the cross product of the row vector and the F vector.
This one's M.
Like this?
Yeah.
Okay.
This is really what you do to make it.
Okay. Any other questions about that one? Then let's go to the weight force. So to get from the about point, the red dot, to where the weight is applied, we'd go negative 0.25 in X. And positive 0.1 in Y. And 0 for Z.
For the center of mass,
Right. And then the weight force is 0, negative 98.1, 0. And the cross product is, that gives you 0, 0, 24.525, I think.
and these first rows, like you do them on the calculator, right?
Yeah. And then I'll go to the force N. The red dot to where N is applied is negative 0.25, positive 0.2, 0. And the force is 0, negative N, 0.
How do you know where N is applied?
It's where I have it touching the body on the free body diagram.
So, could you just put it somewhere else and it wouldn't change?
It would change because that would change, the force wouldn't change, but when you calculated the moment, it would change because the row vector would change.
So, center then.
Why did I what?
I mean,
Oh, because you can always treat the weight as acting at the center of mass. If you're going to treat weight as a single force, it always acts at the center of mass.
okay.
Yeah.
Shouldn't it be 0.1 then? To the center of mass? Not
That's what I did for the weight. I made it 0.1, but this is the N force.
okay. And why is it up higher?
That's just where I have it drawn on that free body diagram where the point is touching the body.
Okay.
To make it clear, you could draw little points, like that. Any other questions? Okay. So now the cross product of these, it's the same, 0, 0, 24.525. So now we've done 3 of these. Now we have to go to the 200 Newton force.
Professor?
Yes.
So I just want to write it down. So we got the moment for mg and n. Where does that come from again?
Once you have rho and F, you're just taking the cross products of those two.
Why the normal force is acting down?
Well, yeah, I mean, I could have named that something else, but that's just, imagine that that there's a frictionless contact with that point, like in a wheel above it or something. Okay. Yeah, something like that. Yeah. We'll see if these numbers work out that way. It might turn out that n has to be negative or something. We'll see. Yeah.
Does the n disappear? The negative n when you cross multiply?
Oh, why did I? No, that doesn't make any sense. Thank you. This should be positive 0.25 n. Okay, that's better. Just cross product of those two gives you the moment. And then 200, okay, so from the vector from the red dot to where that 200 is applied in the corner, that's negative 0.5 in x and 0 for the other ones. So negative 0.5 for x, 0, 0. And then the force is 200 times cosine and sine of 50 degrees. And so this force is 128.56, 153.21, 0. And the cross product is negative 76.60. That's in the z direction. 0, 0, negative 76.60.
Can you explain again how we got the S for the 200?
Yeah. So it's this direction if I draw the coordinate system we're using. That vector looks like this. It has a magnitude of 200. This angle is 50 degrees. So it's 200 times the cosine of 50 degrees, 200 times the sine of 50 degrees.
That's why you put the
Okay? And then the last thing that we have to put in is this couple. Okay? And so we have to think about the direction, but since this moment is produced by a couple, it doesn't matter what the about point is. Okay? So we don't have to think about the about point at all. All we know is that this has a magnitude of 60 Newton meters and it's in this direction. So I'm going to curl my fingers in that direction. My thumb is pointing in the negative z direction into the page. And so that's a 0, 0, negative 60. Okay, counterclockwise is positive, clockwise is negative. Yes?
I was just wondering if your consistence doesn't matter with n is negative z?
Yes, it does matter, and the reason it matters is that this math only works in a right-handed coordinate system, and a right-handed coordinate system requires that the x-axis crossed with the y-axis gives you the z-axis. So if we know that x is this way and y is this way, all the math goes wrong unless you have the z-axis pointing out of the page. Okay. So if you have x this way, y this way, and z into the page, everything goes haywire. Your computer will explode.
So it would have been like going the same way, then it would be out of the base and it would be.
Yep, if it was counterclockwise, then that would have been a positive 60. But since it's clockwise, it's a negative 60. Okay, so I think there are times when you have to do it in like computational chemistry, and there might be some times with like particle physics where they have to but the basic answer is no. I've never taken a class where where I had to use anything but right-handed coordinate systems. Okay, so now we're on the couple. So this is the 60 Newton meters. And the way to put a couple in the table, since it doesn't produce a force and the row vector is meaningless, we'll just cross these two out and we'll put this in as 0, 0, negative 60.
Are you explaining again why? Why is that?
Why is it negative?
No, why it doesn't have a distribution?
Oh, well, because whenever you see a pure moment like this, that's indicating that it's caused by a couple. And couples don't depend on the about point. And the row vector is how the about point gets into calculations. So all we care, and so that's why we cross out the row vector, because it doesn't depend on A. We cross out F because a couple is equal and opposite forces that cancel each other out, so it's just zeros. And so the only place that it matters is in the moment column. Yep.
So we're not giving it like a location at all?
We're giving, well, yeah, we're not giving it a location.
It's just
That's right.
On the like whole box?
Yeah,
Like what?
that's right.
what-
Yeah,
Would
so
it be the same if we like put
Mhm.
it in the middle or put it on the like right corner?
Yeah,
Top right?
that's right. And so this might be a little counterintuitive, but if you, without causing any other forces, put a screwdriver here and twisted it versus taking a screwdriver here and twisting it, the physical effect of that, as long as it's a rigid body, which we're assuming it's rigid, is the same. There's no difference in the physical effect of the locations of those couples. There is an effect when you start thinking about small deformations and stuff, and obviously there's always small deformations, but yeah, so you can make this thing, so if you applied the screwdriver motion here, it would make it rotate a certain amount that way. If you applied it here, it would make it rotate the same amount, you know, it doesn't affect the motion. Yeah.
So the above point, the red dot you put, it has to kind of like, I don't know how to say it, but like, so that when it turns, it's the same as the.
Oh, well, okay, so, right, that's, the red dot is not a physical thing.
Yeah.
It's just a mathematical thing. So, yeah, when you're thinking about these motions, right, so I said you could put your screwdriver here, and it would be the same. The truth is, you could make this a hinge if you get rid of all the other forces and put your screwdriver here, and the motion would be the same. Or you could put your hinge over here and it would be the same. It's weird. It's a little hard to wrap your head around because we're not used to, I mean, you think about what would actually physically happen and there's gravity and stuff, but in the very simple mathematical world, yes, those would behave exactly the same. Yeah. And I mean, even in our world, they would behave similarly for small motions and stuff, but okay. So now we're going to Newton's laws. So Newton's second law, we're going to take all the forces in the F column and add them up and set them equal to 0. And I'm going to leave off the Z components. Yeah, right. So I guess I'm going to do this. I'm going to cross this out, this out, this out, this out. And then in the moments, I'm going to cross out the X and Y's. And we'll just leave the components that matter to us. So for the forces, we have Rx, Ry, plus 0, negative 98.1, plus 0, negative n, plus 128.56, 153.21 is equal to zeros. My computer needs to rest for a second. And then we'll go to the moment equation, rotational Newton's second law, and add up 0 plus 24.525 plus 0.25 n minus 76.60 minus 60 is equal to 0. And this is 3 equations for 3 variables. And so this is solvable. Let's see. So
RX is pretty obvious.
that's true. So n is, so we have 76. So for n, I got 448. .30.
And did you do use your calculator to find that?
That one I just use the one equation to solve for n. There's only one variable in that one. But yes, you always can use reduced row echelon form. And then, so now we'll go to, so we have Ry minus 98.1, minus 448.30, plus 153.21 is equal to 0. And we get that Ry is 393.19. So there's our n. And then our R vector is negative 128.56, positive 393.19. Okay, so that's how couples come into these calculations. Let's do another quick one, and I'll just I'll do one where the math is simple, and we'll just see how a variable couple comes into the problem, because that's something that we're going to get. So let's say that we have let's make the body a circle with a radius of 0.5 meters. And let's say that the mass is 20 kilograms. And we have an unknown force here. I'll call it R. And we have an unknown couple here. I'll call it MR, reaction moment. And we want to calculate those loads. Okay, so a free body diagram. The weight acts at the center of mass. So that's 20 times 9.81. And then we have these two forces, two loads, R, and then the pure moment, the couple MR. And then rho, force, moment. I guess I'll put my about point here. Okay, so first the force R. This time, since in two-dimensional problems, we're always going to cross out the z component of the force, and we're always going to cross out the x and y components of the moments. I'm just going to, that's all I'm going to keep from the start. Okay, so the rho vector for R is 0, 0. The force is Rx, Ry. The z component of the cross product is 0. The weight force from the red dot to the center of this circle is 0.50. The force is Rx, Ry. The cross product is 0.5 Ry.
Isn't it negative?
Is that just the?
Oh, God. Yes, this is just the weight. Thank you. So this is 0, negative 196.2. So the cross product is negative 98.1. And then the last one is the moment. So we don't care about these. And the z component of this moment is just mr. And so now you have Newton's second law that says Rx, Ry plus 0, negative 196.2 is equal to zeros. And the moment equation says negative 98.1 plus mr is equal to 0. And so we get that R is 0, positive 196.2. And mr is 98.1 Newton meters. Okay. Does it make sense that for this to be in static equilibrium, so what we got is a positive moment there? Okay. Does it make sense that you would have to apply a counterclockwise moment to keep this in static equilibrium? Our about point is, like, think of the about point here, you know? That's producing that's trying to make this rotate around the about point clockwise. And so to keep it from doing that rotation, this thing has to apply a moment that's counterclockwise. So yeah, that makes sense. Okay, that's all. So I think I have 2 or 3 problems I can give you. Yeah, and then we'll go into joints next time.
Wait, what? On the test on Monday, will rigid body be on it?
We have a test on Monday. Good question. I will let you know on Wednesday. I don't think there'll be any. I have to think about it.
Maybe like an easier one?
Maybe an even harder one, to be honest.
Why?